What's up, everybody? Today we're doing USACO 2019 January contest at the bronze level. Problem number 2, sleepy cow sorting. Farmer John is attempting to sort his N cows, where N is between 1 and 100, conveniently numbered 1 through N, before they head out for pastures for breakfast. For example, here I've got Farmer John, and if I had N equals 4, then my cows would be numbered 1 through N. Currently, the cows are standing in a line in the order P1, P2, P3, up to Pn. P1 will refer to the cow in the first position. P2 is the cow in the second position, P3 is the cow in the third position, P4 is the cow in the fourth position. But there's no guarantee that cow number 1 is going to be in P1. So when they give you this, that the cows are numbered from 1 to N, and they're in position or permutation 1 through N, they may be in a different order, and you're going to see that that's the case as this problem goes on. Farmer John is standing in front of cow P1. I've already set this up. So in front of the cow in position 1, however, not necessarily the cow with the 1 written on it. He wants to reorder the cows so that they are in the order 1, 2, 3, up to N, with cow 1 being next to Farmer John. The cows are a bit sleepy today, so at any point in time, the only cow paying attention to Farmer John's instructions is the cow directly facing Farmer John. And that's the cow in position 1. These other cows are looking around, they're not paying attention. This is the only cow that can be given instructions to. In one time step, he can instruct the cow to move k paces down the line, for any k in the range of 1 through n minus 1. The cow is going to move at least 1 pace down the line, up to 3 in this case, 3 paces down the line. It's 3 because n minus 1 is 3. The k cows whom she passes will amble forward, making room for her to insert herself in the line after them. If k was equal to 2, this cow will go back 1 step, and this cow will walk forward. Cow goes back 2 steps. Cow walks forward, leaving space for her to insert herself. Very much like an insertion sort. If you've done sorting, that's actually really helpful for a lot of these kinds of problems, understanding the idea of an insertion sort where it removes, slides, and then reinserts. That's why it's called an insertion sort. For example, suppose that n equals 4, and the cows start off in the following order, 4, 3, 2, 1. The only cow paying attention to Farmer John is cow 4, in P1's position. If he instructs her to move 2 paces down the line, 1, 2, the order will subsequently look like 3, 2, 4, 1. 3, 2, 4, 1. Okay, it's always important to make sure you understand the mechanics of the problem. A lot of times people will go through this too quickly and misunderstand the initial mechanics and spend a lot of time writing code that isn't even solving the correct problem. Now, the only cow paying attention to Farmer John is cow 3, who is now in position 1. So if the next time step, he may give cow 3 an instruction and so forth until all the cows are sorted. Another important thing, this particular instruction for cow 4 to go here doesn't work towards the solution. A lot of times when they give you examples on the mechanics, they're not showing you how the problem could or should be solved. Also, very often the sample input they give you is very simplified and will hide a lot of the potential caveats, or will be set up in such a way where you'll coincidentally get the right answer for the wrong reason. That's why we have to create our own additional data, and we'll get to that in a second. Farmer John is eager to complete the sorting so he can go back to the farmhouse for his own breakfast. Help him find the minimum number of time steps required to sort the cows. This is another very important thing, minimum number of time steps. They're not asking you what those steps are, and that is the key to this problem. They're asking for the minimum number of steps. That's it. And we're going to find that there's a way we can massively optimize this problem by not worrying about what the actual moves are and just figuring out how to count how many steps there are. So for the input format, the first line contains n, that's how many cows there are. The second line is n space-separated integers of which cow is in positions 1, 2, 3, and so forth. The output format should be the number of time steps before the n cows are in sorted order if Farmer John acts optimally. So for example, if the sample input has 4, that means there's 4 cows. On the next line, we've got 1, 2, 4, 3. That means the cow in position 1 is cow number 1. The cow in position 2 is cow number 2. The cow in position 3 is actually cow number 4, and the cow in position 4 is cow number 3. The number of optimal steps in order to sort this is going to be 3 steps. I always recommend having a good way to visualize. I have a couple different ways to visualize this problem. One of the ways we can visualize the problem is with toy cows, obviously. If you're playing cards, I use Uno cards. I also have little numbered chips that are from a bingo game. Anything where you can get it out in front of you is really helpful. Drawings are okay, but the tactile effect of having physical objects that you can manipulate is a lot quicker of a way to really get a feel for how the mechanics will work. So let's start by just kind of playing with these cows a little bit. I've got 3, 2, 4, and 1, and I want to get them in order. So we're going to kind of try to think about the mechanics of this. Well, 3 has to go between 2 and 4. So the first thing you might think is, okay, well, I'll put 3 between 2 and 4. Well, the problem is 1 is still at the back here. And all these cows are eventually going to have to move after 1, which means I'm going to have to move cow 2. I'm going to have to move cow 3 again a second time, and then move cow 4. Now, let's think about the implications of moving this 3 cow twice. When I first moved 3 back and then moved 2 back, 3 had to go behind 1. So moving 3 between 4 and 2 didn't do me any good. I want to try and do this in as few time steps as possible. So you really want to be thinking to yourself, where's 3's final position going to be? And it has to be behind 1, which means 3 should go behind 1 on the first step. Once we've got that, we kind of have something that's a little more visual to work with. I've got my 1 and my 3 here, and I want to get these cows to be around those cows, because these cows are like done, basically. So when I give cow 2 instructions, cow 2 is going to go between 1 and 3, and cow 4 is going to go at the very end. So I have that in 3 steps. For the sample input, they gave us 4 cows with 1, 2, 4, and 3. 1, 2, 4, and 3. When we're thinking about the final position of the 1, we have to be thinking in terms of where can I move it so I'll never have to move it again. And again, it kind of seems like putting it next to the 3 here will give us the context for moving 2 and 4 around those cows one by one. Now, whenever you're doing any kind of a sorting algorithm, whether it's a bubble sort or an insertion sort or a selection sort, they sort of will accumulate segments where you know that this area is finished and where we're going to be building around that. When you do a bubble sort, for example, you're going through looking at neighbors and deciding, are they out of order? Okay, 2 and 1 are out of order, so we swap them. Are they out of order? 2 and 4? No, they're not, so we leave them alone. 4 and 3, are they out of order? Yes, they are, so we swap them. Once we've done that, what we're doing is we're building a sorted collection at the back and working our way to the front. Selection sort works in a similar way by going through and finding the cow that is the smallest number and selecting it to move to the front. And then likewise, you're building a sorted section at the front. That process of building a sorted section is exactly the mechanic that you need to use for this problem. You'll have to recognize, when I have all these cows, which section is my sorted section and which section is my unsorted section. 2 and 4 are sorted. 3, 2, and 4 are not. So I'm going to switch over to some tokens. We want to make sure that we can do this with a larger test case. Remember, we're trying to build a sorted set to the back. And the sample code, the sample input they gave you, was a very similar situation. They purposely put the last 2 reversed and then the first part here so that you would have to try to figure out how do you plan around this. And really the reason why is there's always at least one thing to insert around. In this case, even though it's only the 4, we're building around the 4. We should only need to make 4 movements. We should only need to do 4 movements to build around the 4. 1, 2, 3, and that's in 4 moves rather than 5. Okay. In the case we have numbers at the end, like for example, 1, 3, 5. 1, 3, 5 are already sorted. And the more of these you do, the more you'll see how this is happening. And what we're doing is we're taking the unsorted set and inserting it around the sorted set. So how do you know that 1, 3, 5 are sorted? Well, that's very easy. 3 is less than 5. 1 is less than 3. But 2 is not less than 1, which means these are in order, 1, 3, 5, and these are not. And remember, I told you only need to say how many moves it's going to take. Because I have 2 things that are not in order, this is solvable in 2 moves. 1, 2. And that's all there is to the problem. You don't have to make the moves. All you need to do is count from the back how many things are sorted. And worst case scenario, when they gave you this kind of trick problem, if I've got 1 number only, and then this one's bigger than it, then these 4 have to move. Uno cards are another good option if you don't have bingo chips lying around your house. I actually got these specifically to do computer science problems. But Uno cards are great. I'm going to start with just 5 cards. And if you think about when you pick up cards, if you play cards, a lot of times what you do is you try to figure out, how do I insert my cards around the parts that are already sorted? So I've got 1, 3, 4. If I wanted to put these cards in order, I would probably take the 2 and put it here. And then I would take the 5 and put it at the back. And that's actually the exact algorithm that we use for this problem. Let's try it with a couple more cards. It's not random enough. It's never random enough. We're gonna cheat a little bit. Okay. 4, 5, 1, 8, 7, 2, 3, 6. 2, 3, and 6 are sorted. 4, 5, 1, 8, 7 are gonna have to move. As far as the algorithm goes, in order to solve this in linear time, all you have to do is count through and figure out at what point did you not have an increasing set. And actually, we don't even have to store this when we're doing the read. All we have to do is every time we have a number decreasing, we reset our counter. So I'm gonna use my bingo cards here just as counters to count how many cards there are. I read the 4, the next number is a 3, that's decreasing. Next number is a 1, that's decreasing. Next number is a 6, that's increasing. Let's add 1 counter. Next number is a 2, set back to 0. Next number is a 5, that's increasing, we add 1. Next number is a 7, that's increasing, we add 1. Next number is an 8, that's increasing, we add 1. So I counted 3 cards that were bigger than the card to the left of that, which means that I've got 4 cards that don't have to move, which means I have 4 cards that do have to move, 8 minus 4. Let's change it so that we're gonna take this, make it a little bit smaller, 2, 7, 8. Okay, so again, 5, 4, 3, 1 is decreasing. 6 was bigger, so we add 1 to the counter. 2 was smaller. 7 was bigger, we add 1 to the counter. 8's bigger, we add 1 to the counter. It means there are 2 cards that are bigger than the one next to it. We add 1 more, that puts us at 3 cards. 3 cards don't have to move. There are 8 cards, so 8 minus 3 is 5. 5 cards have to move. Last thing, what happens if I only have a single card at the end that's sorted? So 5, 4, 3 is decreasing. 6 was increasing, so we add 1. 2 is decreasing, we take it away. 7's increasing, we add 1. 8's increasing, we add another 1. 1's decreasing, we take it away. We add our 1 chip back at the end, and we've got 1 card that doesn't need to move. And that's it, that's the algorithm. I'll see you for the coding section. All right, so we're gonna walk through the coding solution for this. This is one of the older problems. The older problems had input files. In this case, we have to have a file called sleepy.in, so we'll talk about how to make a file reader for each of the languages. You only really need that for the old problems if you want to submit them to the website. It's not super hard to do. It's very similar to the input you're going to be used to from getting from the console. So we're gonna walk through that process as well. I'm going to first do this in C++. So we're going to do nano. We're going to have 4, and then it was 1, 2, 4, 3. 1, 2, 4, 3. Sleepy.in. I'm going to do touch sleepy.cpp. Okay, first up, C++ solution. We're gonna do IOStream, we're gonna do fstream. A note about coding style: doesn't have to follow what we consider to be proper or good design techniques, it just needs to be fast. So I'm gonna do ifstream, fin, sleepy.in. First thing I always like to do is just make sure that I've got that connected correctly. So I'm gonna do int n, fin n, cout n. Okay, so we're gonna do a sanity check real quick and just see if we're able to read this file. We should be able to make sleepy and then /sleepy. And I got 4, that was reading in n and printing out n. And cat sleepy.in is in fact what I have is for the first number. Okay, so my goal now is to create some sort of a loop. I less than n I plus plus. And then as we read, every time I see a number that is bigger than the one before it, I'm going to count that as 1. So we're going to do int count equals 0. Actually, I should start this at 1. Previous, fin previous. I'm going to try and do this without storing them because I shouldn't need to store them. I can do this in linear time, left to right in one pass. You could also read them into an array and then go back and do a second for loop, but I prefer to avoid that if possible. So we read in whatever the previous number is. That'll be in this case the first number, the 1. And then for the rest of the numbers, anytime I have a number that's bigger than the previous, then I'm going to count that as 1. So int next, fin next. If next is bigger than previous, then count plus plus. Else reset count back to 0. And then previous equals next. Finally, we will report the count. Remember, it's count plus 1 because we're always counting how many numbers are bigger than the one before it. If there's no numbers bigger than the one before it, then that means the last number is the only number we can use. If I've got 1 number bigger than the number before it, then I have 2 that are in order. And so what I'm going to output actually is going to be n minus that. We take the count of how many we're increasing, we add 1 to it. That's how many cows are in the sorted set. And n minus that is what our final answer should be. Let's go ahead and run that. Redo the make, rerun the code. 4, 3. I'm going to take this extra output out, cout, and cout. Finally, because this is a file stream, we have to fstream the information out rather than cout. So ofstream out sleepy.out, out this thing, make, run, and then cat sleepy.out, 3. All right, let's see if we did it right. Sleepy.cpp, and then that's all we would need to submit. Piece of cake. All right, let's do it in Java. Import Java IO file, import Java util scanner, import Java IO.printWriter class sleepy, public static main string args. And again, the first thing I want to do is just a quick sanity check to make sure I can read the file. We do int n, we're going to create our scanner, new file, sleepy.in. Now this ordinarily throws an exception. In a real program, you would want to do a try catch. But for these, we don't have to worry about that. We just put throws exception. You don't even have to specify what kind of an exception. It would be a file not found exception. But again, in the USACO problems, we don't really have to use proper design. The goal is just to get code that runs as fast as possible. Sc next int. We're going to do system out println n. And then let's go compile that. Java C, sleepy.java, and then Java sleepy, and I should see a 4, and I do, so that's good. We're off to a good start. First thing I want to do is set up my previous variable, because I'm going to compare every number to the previous number to see how many are bigger than the one before it. So previous will be sc next int, and then I'll start my for loop. I equals 0, I less than, actually starting from 1, I less than n, I plus plus. Int next equals sc next int. If next is bigger than previous, then count plus plus, oh, I need to make count. Count starts at 0. Otherwise, we start the count over. Previous equal next. Finally, at the end, we'll report system out println the number of cows that exist minus the count that were bigger than the one before it, plus 1 for the last cow. And I'm going to capture extra parentheses around this. Again, that's not strictly necessary. It's just as a little easier to read. We're going to recompile that. We're going to rerun that. Okay, and I got my n's can come out. Printed out 3, which would have been the answer. So now we just got to write the information out. Print writer pw equals new print writer new file sleepy.out pw.println this thing. Recompile, rerun. Cat sleepy.out should have a 3 in it. Ooh. Oh, I didn't close the print writer. pw.close. Java C, Java sleepy, and then cat sleepy.out. Looks good. I'm going to pick Java. We're going to choose our file, sleepy.java. Submit the source code, and let's see how we did. All right, piece of cake. Okay, finally moving on to Python. Now, file readers in Python are a little trickier than they are in C++ and Java. With C++, you can always just grab the next number out of the file. Same thing kind of goes with Java, and these input files are designed to work like that. Python's not quite so comfortable reading individual pieces out of the file. We usually do it a line at a time, so our approach has to be a little different. But there's a couple tools you can use to kind of expedite this. Sleepy.in and equals f dot strip 3 sleepy pi. Okay, so we got our first sanity check. We don't really have any imports for Python. It's a lot more streamlined. We just open the file. I can read the line and strip it. One thing though to point out is this is not an integer by default. This is a word. So if I do n+1, oops, and I run that, it's not going to like that. I have to specifically convert this to an int. Next thing, we got a whole list of numbers. We're not going to be reading these one at a time. We're going to have to read it and pre-process it. So we're going to do numbers equals f.readline.strip.split. Okay, so what we're going to do in order to make this work, let's say like I have a line that's like something like that. So if I were to do line.split, that gives me the numbers as strings. If I want to turn those into integers, I need to map the int function across line.split. That's going to give me back this map object. In order to turn this into a list, I can call the list function on it. Now I have a list of integers. So the numbers are going to be list of map of int on f-read line strip split. It's kind of a mouthful, but then we'll go ahead and print out numbers here to show how that works. Numbers. You can, I mean, again, you're not going to have to do this on any of the new USACO exams, most likely, because now we've worked to getting regular input rather than file reading. So this is something that we used to have to always do, but we haven't had to do this for a couple years. So once we have our numbers, the rest of the process is pretty much the same. Count equals 0 for I in range 1 to n. If numbers at I is greater than numbers, this is a little different because we don't have that previous, numbers at I minus 1, then count plus 1, else count equals 0. So we do count plus 1 for the last number because there's always one more, and it'll be n minus that. So I want count plus 1 because that's how many cows are in increasing order, which means the number that need to move are n minus that. So I run that, and I've got 3. Last thing is we need to make this into a file writer. I'm going to close my reader from up here, f.close, about, let's f in and f out so it's consistent. About equals open sleepy.out for writing, about.write this thing. Here we go. Let's just submit it and see what happens. Okay, Python 3, choose sleepy.py, submit solution. One other thing I want to point out is the amount of runtime is kind of interesting. So this is sort of a smaller file, but you'll notice the Python does it in about 70 milliseconds for each of these problems. I want to compare to Java and C++. Now, this doesn't have a direct bearing on your ability to pass the test. All these questions can be passed with any language. But it is important to note sort of the relative speed of each of these. So notice the Java machine is actually slower. Now, that's a little unexpected because Python's a scripting language and Java is a compiled language. But Java has a virtual machine it's got to run things through. So for smaller problems, Python actually starts executing a little bit faster than the Java does. For the larger, more complex problems, you notice that usually the runtime on Python is the slowest of the three. But for small problems, Python's actually pretty quick. But comparing 70 to 110, I mean, that could have been an inconsistency in a lot of things. So I do want to point out something about C++. C++ sort of seems to be one of the more popular languages. It's the language that I usually go to for these kinds of problems. So you'll notice we got about 60 milliseconds on Python and about 100 on Java. We're at 2 milliseconds on C++. Now again, that doesn't increase your chances of passing these problems because they do scale the time. But the faster executable time has a couple very small advantages. One of them is that you get your response back faster from the grading server, which is kind of nice. Another thing that's sort of a minor bonus to it is in C++, even though the syntax is a little hard to look at, there's not a lot of typing and it's pretty simple. Compared to Java, there's a little bit of extra framework you need, which is, not a big deal, but it's a little more ink on the page if you kind of look at the two. This is more, you have to type more to get the same sort of results. And Python's very short, but you notice these lines are very dense. There's a lot happening here. And because of the way the file readers are set up, dealing with this, not being able to just read an integer out, but having to read entire lines and split them is a little bit of a hoop to jump through. So again, you can use any language you want. A lot of the official solutions are released in C++. Let me see what they did for the official solution for this one. Let's see if it shows here, solution. Platinum level, that's in C++. This one's in C++. C++ again. Yeah, so just because as you go, you're going to see a lot of solutions provided in C++, and it does seem to be a fairly popular choice at the higher levels. A lot of times at the bronze level, people are using Java because they've just come out of AP or they're in the middle of AP. Making a transition into C++ is something worth considering, though. And again, it's not that difficult once you have a good handle on Java. But as far as collaborating with other people, as far as reading the solutions, and just as far as, again, the speed at which you can type the code, the amount of time it takes to type this is a little bit less than the amount of time it takes to type this. And you do get the responses back from the autograder a little bit quicker, which is kind of nice. It's just shaving off a second or two, but it does help a little bit. So, all right. So that is sleepy cow sorting in C++. Java and Python. I hope you enjoyed it, and stay tuned for my next video.